Okay, line M1, learning task 4, we're going to talk about paralleling alternators. And particularly, once again, we are dealing with three-phase alternators. We talked about this briefly in second year. Now we're going to go and cover it in depth here in our third year. Why do we put alternators in parallel? Well, we're going to put alternators in parallel anytime that we need to go and increase the amount of load that we are going to go and put out. What we're going to go and see inside of any type of a dam, if you can imagine, the dam itself is going to be built in between a couple of mountain peaks, etc. We're going to hold water behind that, and then at the bottom of that, we are going to go and have the actual powerhouse that we are going to go and run all of these alternators inside of. What you'll see inside of an actual powerhouse is you would go and see a whole row of alternators. They're not going to just run one big alternator off of here. They're going to run a whole pile of different alternators. And in a lot of cases, they've already got rough-ins for, future ones as well. They're going to have to put the concrete in place. They'll have built it so that they're ready to be able to expand that system as needed. The reason for this is that throughout the day, we are going to go and have peak times that we are going to go and deliver more load out to the province and require more load from the province in return, or require more power output to feed the province in return. What we see is, relatively low amounts of power, and then right in the morning, about, from 7 o'clock until about 8 o'clock, we see a little bit of a spike, generally speaking, as people get ready for work, showers, hot water tanks, cooking, things like that happen. Then it's going to be a little bit higher during the day because we are going to go and have offices and buildings that were shut off during the night that come on. We're going to see a peak again around noon where people start to do a bunch of cooking and things like that once again. And then it's going to go and taper off, and then we're going to go and see a little bit of a dip just around the time that people are heading home, and then we see a larger peak again around supper and through the rest of the evening because people are running all of their lights, they're running appliances and stuff like that to go and cook, etc. So what we have is throughout the day, we are going to go and have certain levels that are going to be able to be hit by certain alternators that are going to get brought online as we go through. And so what we might have if we have a given amount of power is that to supply this, we only need to go and supply out of one alternator. As soon as we get up to this point, we start coming over top of that. We're going to bring a second alternator online. We're going to bring a third alternator online. We'll bring fourth and fifth, to go and get over to the peak. Then we'll drop the fourth and the fifth. We'll run off with the three, etc. We'll bring them back on, etc. It's this dynamic system where we are changing them as the day goes through. The better that we can run them, the closer we can run them to full load, the better the efficiency of generation that we are going to go and get out. Because otherwise, we're just going to be fluxing out the fields with very little power that we're going to go and take out. Remember, it does still take power to go and create that field for us to go and operate through. So rather than having one giant machine with a massive magnetic field that we're just going to continuously be changing around, playing around with that field, we're just going to bring on individual smaller alternators as we hit our different peaks. The other reason that we might have alternators is maybe we're using these 5 that I just went through over here out of this powerhouse based upon what this powerhouse is actually supplying. But I'm going to go and have the ability to go and add in a couple more if the area demand. You've got a town or a city that is really starting to go and build, and so that you got to go and create infrastructure that's going to be ready to go for it. Last of all, having multiple ones like this means that I'm going to be able to go and do periodic maintenance. Trust me, there is a major maintenance program that happens inside of all of our powerhouses and dams because we cannot afford to go and have a complete dam shutdown, right? So what we'll do is we'll take one alternator offline, we'll replace it with a different one that's going to come online, and then we can take this one out, we can pull it, rebuild it, get the thing ready to go again, drop it back in. So we're just going through this continuous cycle of, alternator to alternator to alternator, that these things are going to be taken offline, maintained, put back into service, and we move on to the next one. Because we have got all of these different alternators, we do have to go and bring them online together so we don't end up with a shock on our system. And in order to do that, we are going to have to hit a number of things that are going to go and be the same. They give you on your page 27 there, or at the beginning of this learning test, they give you a list of 5 different things that need to all be exactly identical for me to bring these things together. First of all, the terminal voltages of both of these have to be equal. So I'm going to go and change my excitation, the field, to go and bring that up. Secondly, I'm going to have the same frequency. This is going to be done through the speed of the prime mover. And third, I'm going to go and have these things in a phase sequence that is going to go and be A, B, C, or C, B, A. I just have to make sure that my phase sequence matches whatever I'm bringing online with whatever is going to go and be existing. The next thing that I have to do is I have to worry about stepping. Number 4 here says they must be in step or in phase at the moment of actual connection on here. We'll go through what that looks like in a second, but it's relatively, simple step that we have where we just need to make sure that line 1 is at the exact same line 1 value as something else. We'll use a couple analogies later on for that one. We'll come back to it. Right now, let's just pass it over right now. The last thing is the prime movers must have relatively the same speed and load characteristics. This just means that as they get loaded down, that they have to go and bog down the same. You would not want to go and have, one alternator that's run off of a dam and another one that's going to necessarily be run off of a gasoline engine and then another one that's going to go and run off of a diesel engine, because they're all going to have different ways that they deal with torque and with loading on there. And as I change the torque, I'm going to go and change the loading of these. What we have for bringing these things on is going to be 2 main methodologies. Both of them are quite visual. One of them is going to be called the 3 dark method, and the other one is going to be referred to as the 2 bright, 1 dark. But before we do that, let's just go and take one of these here. We're going to take that out. We're going to talk about the whole idea of synchronization or of being in step. When we dealt with transformers, we talked about the importance of making sure that we followed standards, that I was going to have, ABC rotation, anything that parallel on from one to the other would be the same. And the reason for that was that we wanted to go and make sure that whatever we create is going to go and be exactly equal. So I'm going to go and have an A phase. I'm going to draw them out over here. We're not going to do vector analysis, but we're going to draw them out just as arrows over here as vectors. Off of one of my systems, I should have something that is going to go and look like that. I'll just select these and group these. Perfect. And Eli, get out of there. Perfect. Okay, so we got 2 of these over here that are going to go and be identical. What we need to do is we need to make sure that before we parallel our systems, we're going to be identical. So I'm going to have the same values of voltage, I'm going to go and have the same frequency of these, and I need to make sure that they're in step. Now, what the in step means is that actually these things rotate around as this thing is driving through. We're going to go and have rotation. Remember that all that we're talking about with these vectors is that it's going to be something with speed and direction, and a phasor is going to have speed, direction, and rotation. That's really what we're dealing with on all of these. What we need to do is we need to go and line these 2 up so that when I snap one over top of the other, they look the same like that. What we don't want to have happen is I would not want to go in parallel when I am, sitting at this point over here, where I've got all of my voltages that are going to be directly opposite one to the other. Because if I would go and close in at this point, even though they all have the same values of voltage, so this is still going to be 120 volts. This here is also still going to be 120 volts. Even if I would have these both at being 120 volts, or 120 volts that instantaneously are opposite to each other. And so it would be really, really bad if I closed in at that point, because now I'm going to go and see a line-to-line 240 volts short on that phase, as well as I'm going to... Eli, get out of here! All right. This is annoying. I got a stupid cat in here with me right now. Nothing much I can do about it because it's winter and he's in the garage. But anyways, back to where I was before he destroyed what I was talking about. We want to make sure that these things are going to go and be operating at the exact same time with the same voltages, and they're going to go and be in phase. And the way that we do that is we look at these 2 vectors and we say that we want to go and make sure they're rotating at the same time, but one of them has to be rotating just a little bit faster so it can catch up with the other. And then right as it passes the other one, click right there, is where we would want to, boom, hit that synchronization. And what we're doing is we are just bringing it really close to the same values of frequency. I want you to go and imagine, once again, let's say that we had a circular racetrack over here, okay? And you've got a car that is going to be on that racetrack. So, man, I cannot draw a car here for the life of me. Start with the wheels. Okay? We've got a car that is going around on that racetrack. And we've got another car that is also on this racetrack. We're going to use this racetrack analogy a fair bit when we deal with our motors and stuff like that later on. If this car over here is traveling at 100 kilometers an hour, and this car over here is going to be at 0 kilometers an hour, what's going to happen is that we are then going to go and have this massive difference, right, from one to the other. They're both cars. They both have the same mass, the same acceleration, in the same way that, these vectors over here have got the same voltage and magnitude and stuff like that. But what's different about these two cars is if this one here is going 100 kilometers an hour, it is going to go around that track, let's say call it 1 kilometer track, 100 times inside of 1 hour. If this one over here, the lower car, would be operating at a lower value of speed, 0 kilometers an hour, it would be really damaging if when this car was passing that car, if I tried to hook them together. Okay, just imagine I had a grab hook and I threw it out of the one that's driving past. As it hooks onto this one over here, boom, you're just going to have a bunch of tearing and stuff that's going to go and happen. It would be much better if I were to go and get these two if I needed to go and get these two tied together, I would want them rotating at almost the same speed. Now, I wouldn't want them both at 100 kilometers an hour, because if they're at the exact same speed and one car is over here, it's upside down, see, it's on the opposite side of the track over here. But if one car was over here and the other car was over here and they both the exact same speed, they would always stay opposed from each other. We get that thing where the volts are opposite of each other. What I do instead is I bring this one here to 99.9 kilometers an hour. Which means that it's going to be going a little bit slower, which means that this one over here is going to go and slowly pull ahead, and then it's going to start to go and catch up. And we're just going to wait, and we're going to watch until this one here, the one that's going 100 kilometers an hour, has just about caught up, and as soon as it just catches up to the point that's even, boom, that's the point where we would lock it in, and where we would then just adjust this one so that it's going to be going at the same value. So the same thing when we're dealing with synchronizing, we're going to go and have both of these rotating. Once again, just imagine that this thing here is rotating, and then imagine that I've got this one here, which is rotating just a little bit ahead of it, but it's a bit slower, okay? So both going around in a circle. This one here is my existing one that's operating at 60 hertz over here. This one here is going to be my other one, the one that I'm paralleling, and it's going to be operating at 59.99. 59.99, which means that this other one is going to be slowly catching up to it. And what happens is my 60 hertz is going to be catching up, and the second that it catches up, we slam it in. Now I want you to take a look at the tips of the arrowheads. Right now, the tips of the arrowheads, there should be 0 volts of difference between the tip of either of my arrowheads to each other. Both of the black arrowheads are at the same point, both of the red arrowheads are at the same point, and both of the blue are at the same point. These represent values of voltage. Well, if they're both at the same point, is there any potential difference? Absolutely not. So we would know that we would be at 0 volts. So I would have from one line to the other 0 volts. Over here, if I would have this happening right now, I would see that from the tip of this one to the tip of this one, there's going to go and be some displacement. Therefore, there has to go and be some volts that would be across it. What we're doing in the 3 dark method that we're going to talk about first is all we're doing is we are waiting until the one that is behind, the 60 hertz one here, it's whipping around faster than the 59 hertz. We're going to wait until it goes and gets to the point where these tips are at the exact same point. When they get to the same point, boom, we're going to be all dark because there's no potential difference between any lamp. And at that point, we would want to go and synchronize. Here's how that looks. First of all, we're going to start by saying this is going to go and be my online alternator. It's already operating and it is powering my load bus. I'm now going to go and bring on this alternator number 2 over here. So what I do is I'm first going to go and have, I see I've got switches. These switches are open and across each of the switches. So going from my line, we're going to call this one here A. This one here has got a solid A connection all the way down to here. Going from that line A to this line A, I'm going to go and place a lamp across that open switch. I'm going to do the same with B, C, etc. I'm not going to go and draw the other ones out. We'll keep it as clean as we can. But what you should see on here now is that we're going from A to A. What we'll have is we're going to go and first of all make sure all the lamps are coming on and off together. If they're all coming on and off together, it means that my phasing is the same. Take a look at it. All the lights would be developing value voltage. They'd be getting brighter, 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 brighter. They'd be at maximum brightness, and then they would be getting dimmer, dimmer, dimmer. Just watch the tips, not the center. Dimmer, 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 and then they would all go off together, etc. That's going to be our three dark method. So we're going to make sure all the lights are coming on together, all the lights are coming off together. If they aren't coming on and off together at the same time, what's probably happened is that one of my, I'm not going ABC, I might be going CBA. Let me see if I can just rotate this one. We'll try that there. Which over here is going to be a CBA. What I would be seeing right now, watch the black arrowhead right now. The black arrowhead would be getting closer and closer to being 0 volts from one to the other, but I note that the red and the blue arrowheads are still going to be opposed from each other. Looking at this blue arrowhead to this blue arrowhead, we've got voltage across it. This red to this red, we've got voltage across it, but the black is going dark right now. A couple seconds later, I'm going to go and have the reds that are at the same point and the black and blue that are going to be bright. A couple seconds later, I'm going to go and have the red and the black that are going to be bright and the blue that is going to be going dark at that point. So we're going to go and have, two that are going to be bright and one that is going to be going dark. And what we're always going to be seeing is that, I want you to just watch the red and the blue right now. Right now, those two red lines are directly opposite each other and the blue line is close to each other. The blue line is going to be getting further and further apart, while my red line is getting closer and closer and closer. So the blue light would be getting brighter and brighter, while the red would have been getting darker and darker and darker off of that. So going back to my steps here, we're still working on the 3 dark. What I'm looking for is that they're going on and off in unison, because if they're going on and off in unison, that does mean that I have got the same ABC rotation that's inside of there. What I'm going to do then is I'm going to go and adjust the speed of the prime mover for this one over here, number 2. I'm going to bring it close to the same speed as this one so that they're going to be close to the same frequency. And then once I go and get this thing together, I'm going to wait till I have all 3 lights dark. When all 3 lights are dark, that's going to mean that I have at that point got all values of voltage equal. The difference from A to A is going to be 0 volts, B to B is 0 volts, and C to C is 0 volts. So I can close in. Now, the only problem with it is that incandescent lights, we still have a fairly decent amount of voltage across a light at the same time as we close it in, even though it's not actually glowing. Try placing a 9-volt battery across an incandescent light, you're going to still have 9 volts over top of it, but you're not going to see any sort of glow that's going to go and happen. This could mean that we will get some disruptions to the line. So what we can other times do is we will go to the 2 bright, 1 dark. And the 2 bright, 1 dark is once again going back to what we just looked at over here. I'm going to have rotation. I'm going to have differing so that I'm going to have my black is going to stay there, or my red is going to stay the same here, A to A. But then I'm going to go and reference my B, my black, across to C, and my C across to B over here. What I'm going to do with that is I'm going to once again watch my lights. I'm going to bring these things close to the same value of frequency, and I'm going to go and watch these things going around, and I'm going to look for the point where I am going to go and have the light that is connected the same at an equal value of voltage. So I'm looking at the black one over here. Okay, this is the one that we're watching. Right now, I would have 0 volts. The black light would be dark, but my red and my blue would both be equally bright. And if I move past that point, then all of a sudden my red would be getting dimmer, my blue would be getting brighter, my black would be getting brighter, and then my red would get dimmed down to a value of 0, the other 2 would be bright, etc. They're just going to go to this 2 dark, 1 bright. What we're watching for is we're watching for the dark on the line that we have not cross-connected. In this case, it's going to go and be the A1. You're going to close in exactly when this one that is over here, the A line, as soon as this thing goes dark and the other 2 are going to go and be bright, that is the point where you would want to go and close in off of this one. Okay, synchroscope. Synchroscope is better than the lamps because it's going to go and tell us what we have coming in here, and we're able to actually kind of visually see it a little bit better. We'll use these not the very first time that we parallel. The very first time that we parallel, we're going to want to use the 3 lamps just to make sure that we have got the same phase rotation. You could use a phase rotation meter as well, but we would want to go and use those just to ensure it's going to be the same. Once we know it's the same and we turn this thing on or off once or twice, we'll from that point on use the synchroscope. And the synchroscope is just going to go and give us an indexing point. This is going to be the 0 that we're looking for over here. This, when our needle points onto this, that is the point that we want to go and close in. And then this needle is going to go around here in either direction, depends upon whether the incoming alternator is faster or whether the running alternator is going to be faster. Whichever one is faster is going to determine whether it's going to be going, clockwise or counterclockwise. And we just monitor those values of voltage from one to the other. And as soon as we get this needle that lines up right over there, we want to close. Usually you are going to go and close at the exact instant that it's crossing, but if you got a little bit of a delay because you got contactors and switches, maybe a couple of contacts that close a contact that close a contact, you might close in a little bit ahead of that. You do need to have rotation on this. If the needle is staying in one position, it just means that both this and this are at the exact same frequency, 60.1 and 60.1. There has to be a difference because otherwise we're back to that whole thing on the racetrack there where we got a car here and a car here. And if they're at the exact same speed, they will always stay opposite each other, which would mean we would always have difference from them. One needs to always be coming in a little bit slower than the other. What we want to do is we want to go and adjust our frequency. We can adjust, and then we can go and back off that frequency right when this thing closes or gets to here. If you want, you can try and stop the needle on here. If you stop the needle on here, then at that point, go ahead and throw the paralleling switch to go and put these things online. Once we've got the machines online, what we then need to go and do is we need to transfer load, because the alternator that was already running, in this case, we're going to say alternator 1, which was already running, or sorry, alternator 2, which was already running over here. We had alternator 2 that was online already. It was running, it was carrying all the load. We added in alternator 1. The instant we close it in, what we are going to go and have is, we're going to have that alternator that is doing what we refer to as floating online. It's not picking up and carrying its amount of work. It appears to be, it's operating at the same speed, but it's not doing anything. Imagine if you get something really heavy to carry at work. Everybody has worked with that one guy who, when you get 3 guys lifting a transformer or something, you're going to just get this one worker who is going to be like grunting and groaning, pretending he's doing all this work, but everybody knows that they're not actually putting any pressure. They're not doing any lift. They're just making it sound like and look like it because they're moving at the same speed as everybody else. This is what floating online is when it's an alternator. It appears that it's doing something, but it's not actually torquing, giving any sort of a force to it. Going back to that analogy of having 3 people lifting a heavy transformer, same thing. They're all moving at the same speed, but they're all doing differing amounts of work based upon what their power output is. If you could evenly change it, you would go and have some people, lift a little less hard and other people lift a little harder to go and even that out. And we'll do the same when we bring these things online. Once we have brought these things online, then what we'll have to do is we have to go and change the torque value to go and shift the load from alternator number 2, which has been at this point delivering all the current out to these lines over here. We need to shift a little bit more onto this one over here. This is going to go happen by us changing the mechanical power input of the prime mover. So we're going to go and increase the amount of torque that we are taking out of this one over here. We're going to go and decrease the amount of torque that we are going to be taking out of this one over here. And I'm going to be doing that while simultaneously watching both of these ammeters. Once I get both of those ammeters to the same amount of amps, I've got that load evenly shared. When you are trying to go and parallel these things and trying to go and increase the amount of load, make sure that you are going to be changing the actual engine, the torque values that you're going to be changing off the engine, that you're not trying to go and change the voltage values through the rheostat. If you try to adjust it through the rheostat, it will go and change the input, but the reason it's changing the input that we're seeing more current that's going into this is because we're actually raising our value of voltage higher here and dropping our value of voltage over here. It's the wrong way to do it because then we're going to end up with circulating currents that are going to go and happen in between these two. They gave us a couple of vectors, about that explain this whole thing, effective varying the field excitation that we are going to go and have. And they're trying to explain it from engine 1 to engine 2. Ideally, the 2 engines are going to go and be the same. But if I go and if I change the value of voltage and I'm going to go and force more voltage off of this one, a little less voltage off of this one, what's going to happen is that I'm going to go and have a current that is going to be traveling with my voltage inside of one, that's going to be traveling opposite to my voltage inside of another, because we're forcing that thing through. And so what it does, if I change the direction of current through something, is I'm going to go and change, if it was lagging, I'm going to change the one into leading. And we overall get this net effect where I'm going to go and add in this little value of voltage over here. This ER that they list this one, it's the resultant voltage, that is going to go and happen because I've got a current that is out of phase, and so it's going to be seen as lagging for one, dropping the terminal. So anytime we lag, it is going to go and drop. Anytime we lead, it is going to go and raise that value of voltage that we would go and have off of it. What we'll actually see over here, this drawing is maybe just a little bit wrong in the way that it puts it out. E1 and E2, they should be the same value. What it's actually doing is it's shifting where this point is what the current is. So this bottom drawing should be the exact same length. It should just show this point shifted over and part of it being made up of, my ER, etc. Don't stress too much about it. They're just vectors. They don't exist in the real world. They're just ways for us to visualize, physical effects that we're seeing in the real world. The long and short of that whole entire paragraph is just that don't try to change the voltage by increasing the field current, because it's not actually going to go and cause the actual alternators to go and change the amount of load that we're going to go and have off of there. Prime mover considerations, we talked about that at the very beginning, that when we're going to parallel them, they need to go and have the same speed load characteristics. Because they are going to go and be taking the same amount of current off them. We should balance them when we bring them online. What happens is then when we take a bit more current, or we drop away from the amount of current that we're taking, we can end up at these differing speeding characteristics. Just different things can go and deal with changes in the load much more different. The stronger the engine, the less that a change in load is going to go and affect. So it's going to keep its RPMs high, whereas a weak engine is going to be more affected by it. What we have to do is we have to go and make sure that they're going to be similar. Don't try to parallel from multiple different manufacturers together. It's just, generally speaking, going to lead you into problems. Last thing inside this section here that they have over here is going to be hunting. And hunting is just going to be a pulsating or an oscillating effect, causing current to surge back and forth between the alternators in parallel. Basically, one is going to carry a bit more, then one is going to carry a bit more, then one is going to carry a bit more, then the other is going to go and carry a bit more. And where it comes from is it comes off of things that are going to be not mechanically balanced. Generally speaking, what we have is we are going to go and have an engine. That engine is going to go and have a crankshaft, and it's got all those cylinders inside of there. And what it has is every time that there's a little explosion inside of a cylinder driving that crankshaft, and just zigzaggy crankshaft down over here, that there's going to be unequal torque that's going to be put out. So what we'll do is we will go and put on a really heavy, large flywheel in a lot of cases. And the flywheel is then going to go and dampen that. It's going to go and steady that thing out. If I have got either the flywheel that's a little bit off balance, or if, maybe the flywheel is just too light to take all of those out, what I'm going to go and have is I'm going to go and have coasting that's going to go and happen. Basically, I'm going to go and have, a small, call this cylinder here, there's going to be a small explosion inside of that cylinder. That's what an internal combustion engine does. It's going to go and boom, push that thing just a little bit, and then it's going to kind of coast a little bit slower into the next position at which the next cylinder, boom, is going to go and fire, which is going to go and take it faster, and then it's going to go and coast in. And it's going to go and take it faster, and then it's going to go and coast in it. So we end up with these, high speeds, and then it kind of coast down. High speed, then it's going to go and coast down, etc., as we go along through there. It's not good for our frequency. It's not good for our value of voltage, because our voltage is going to go and follow. EG is equal to K phi N. K phi N, which means that as the speed goes up and down, this voltage is also going to go up and down. And we don't want to see that, because then the voltage goes up and down, the current out is going to go up and down as well. What we want to do is we want to go and make sure that this thing stays uniform, and so we're going to have these amortisseur windings that are going to go inside of the main face. And what the amortisseur winding is it is going to go and have, we'll use them on the salient poles, by the way, we're not going to use them on the cylindrical rotors, but it's going to be just a very large coil of wire. And that large coil of wire is going to be welded together. It's going to be mounted on a steel frame, on the actual steel salient pole of that thing, but current wants to travel through the large copper or brass winding much more than it wants to go and travel through the laminated steel. So it's going to just stay inside of there, the current. And what it's going to do is that at any point during which this thing is coasting, it acts as if it were a motor. It basically is going to go and pick up, and it's going to go and try and drive itself. It's going to help to lift it through there. Anytime that we get this surge, where we get an explosion inside of the chamber, there's an explosion in the chamber and it pushes forward, it is going to go and act as if it were a generator, and it's going to go and fight back at that point. So we get a little bit of backfighting, then we get a little bit of aiding, and then we get a little bit of backfighting, and then we get a little bit of aiding. And what that does is the aiding happens during our low speed times, the backfighting happens during our little blips or boosts that we're having, which goes and drops these boosts, makes them a little bit smaller, and the motor effect aids these boosts, makes them pick up a little bit better. Gives us a much more even type of rotation out here. This is not something we're going to add after the fact, something that the manufacturer is going to have placed inside there. Whoever makes the alternator will go and deal with the amortisor. Whoever assembles the whole generator set, we call them just gen sets for short, is going to be in charge of what sort of a flywheel, if any, that they're going to go in place between the alternator and between the generator, the actual engine itself, to go and damp down any irregularities that we have. Okay, that's that for self-test 4, or learn test 4 onto yourself.